Section: Introduction. In this section, we discuss the recent advancements in large language models, LLMs, and their growing use in various tasks like code generation and language processing. However, these modern LLMs often have hundreds of billions of parameters and require substantial hardware resources, making them expensive for individuals or organizations to operate independently. This has led to an increased reliance on third-party LLM inference providers, which raises significant privacy concerns, especially in fields governed by strict data privacy laws or where sensitive information is involved, such as healthcare. To address these privacy issues, researchers have been developing efficient protocols for LLM inference that protect the confidentiality of input data from third-party providers. Many of these protocols utilize secure multi-party computation, SMPC, allowing multiple parties to perform inference without any single party being able to reconstruct the input from the information they receive. Recently, several SMPC schemes have been proposed for LLMs, primarily based on additive secret sharing, which works well for most operations but struggles with non-linearities. Some researchers have tried to overcome this limitation by using approximations for non-linearities, but these can negatively affect performance and are still more costly than direct computations. Others have explored statistical obfuscation methods, which are faster than SMPC but only offer statistical security rather than theoretical security. For instance, some recent approaches have used the properties of transformers to create permutation-based schemes for private inference, where hidden states are shared as permuted data. However, this method has been challenged by a new attack that can decode input tokens from these hidden states, undermining the security of several permutation-based schemes. In our paper, we introduce a new multi-party scheme called Cascade, which is designed to resist the vocab matching attack. Although Cascade is a statistical scheme, it uses token-level sharding for obfuscation. While it does not provide the same rigorous privacy guarantees as cryptographic methods, it is significantly more efficient, up to 100 times faster and with over 150 times lower communication costs, offering a new balance between scalability and security. Our main contributions include generalizing the vocab matching attack to sharded hidden state reversal, introducing Cascade as a multi-party statistical scheme for open weights inference, demonstrating its security against the generalized vocab matching attack, and showcasing its efficiency and scalability. We assume a scenario where a user wants to perform inference with an LLM on a sequence of tokens but lacks the resources to do so independently, relying instead on a set of semi-honest third parties. We also assume that the LLM employs unidirectional self-attention, which is a critical aspect for the success of the vocab matching attack. Section Summary. In this section, we discuss the growing use of large language models, LLMs, for various tasks and the associated privacy risks when relying on third-party inference providers. We introduce our new multi-party scheme, Cascade, which enhances security against recent attacks while being significantly more efficient than traditional cryptographic methods, allowing for scalable inference on modern LLMs. Section: Related work. In this section, we discuss recent cryptographic schemes for secure multi-party computation, SMPC, that aim to reduce the computational burden of handling nonlinear functions in transformer models. For instance, in MPC Former, we substitute the JELU activation function with a simpler quadratic approximation and replace softmax with a normalized quadratic approximation. Although they use knowledge distillation to enhance the model for specific tasks, we still observe a notable drop in performance. To sidestep the costly fine-tuning process, Puma introduces the first SMPC protocol for JELU using piecewise polynomial fitting. However, this method still involves numerous multiplication and inequality protocol calls, making it expensive. To enhance JELU's efficiency, SecFormer opts for a Fourier series approximation with segmented polynomials and also applies knowledge distillation like MPC Former. This approach achieves comparable runtimes to MPC Former while delivering improved performance on downstream tasks. Most related statistical methods we encounter are based on permutations. For example, The two-party scheme perm LLM permutes hidden states at nonlinear components to safely disclose elements to the involved parties. Additionally, STIP, a three-party scheme, allows the model server to perform inference on user inputs without accessing the proprietary model weights, using random permutations of both hidden states and model weights. The Senator scheme follows a similar three-party model but avoids revealing the embedding lookup table and certain unpermuted intermediate results by integrating additive secret sharing from SMPC throughout the self-attention stages. In all these schemes, hidden state permutations are exposed to the party conducting inference. We leverage this observation to challenge the security of these methods through a vocab matching attack. To evaluate the security of our statistical scheme, we will assess the reconstruction quality of learning-based attacks on the exposed shards. The most pertinent attacks in our context focus on reversing hidden states and logit distributions. The first study emphasizes reversing hidden states, while the second centers on logit distribution reversal. Both works fine-tune a transformer-based model to revert hidden states to their original input tokens. The second study does not assume the adversary has access to model weights, while the first explicitly considers a scenario where a model provider performs inference on user-provided embeddings, making it more relevant to our situation. We will also evaluate our scheme's security against a generalized version of the attack that can reverse input tokens from sharded hidden states, which we will detail further in the next section. Now, we describe the basic attack where the adversary receives complete hidden states from a layer and attempts to recover the input prompt. We also introduce a variant where the adversary only gets some hidden states but can search through multiple unknown tokens. In the basic attack, we consider a unidirectional large language model, LLM, like Gemma 2-2 which receives a user prompt such as, "What is currently the most populated city in Spain?" After tokenization, this prompt translates into a list of tokens, including special tokens indicating the start and end of the sequence. These tokens have corresponding embeddings that are processed through the model's layers to produce hidden states. The provider uses the model's vocabulary to compute embeddings for each token and identifies the one that minimizes the error between the model's output and the hidden state. This process continues iteratively until the provider reconstructs the original input embeddings, which can then be converted back into the input tokens using a lookup table. Successful execution of this attack relies on avoiding collisions, as these could prevent accurate recovery of the original tokens. Section Summary. In this section, we review recent advancements in secure multi-party computation, SMPC, schemes aimed at optimizing nonlinear operations in transformer architectures, highlighting various approaches like MPC Former and Puma that attempt to improve efficiency while addressing performance degradation. We also discuss the vulnerabilities of existing permutation-based schemes to attacks that can reconstruct input tokens from hidden states, emphasizing the need for robust security measures in our proposed methods. Section: Sharding Generalization. In this section, we discuss a broader version of the basic attack, as outlined in our pseudocode. This applies to situations where the provider does not have access to all hidden states. For example, if they only receive certain hidden states, like the 3rd, 5th, and 10th, they cannot recover all input tokens. Specifically, since these hidden states do not relate to the 11th and 12th tokens, we cannot guarantee their recovery. However, our generalized attack, which requires significant computational effort, allows us to recover all tokens that the last hidden state depends on, which includes the first 10 tokens. Initially, the provider cannot decipher the first token because they lack the first hidden state. Yet, by generalizing the first step, they can derive the first 3 tokens from the third hidden state. This is possible because the first 3 hidden states correspond to the first 3 tokens, and assuming no collisions among the possible combinations, the provider can recover these tokens in a limited number of attempts. Next, using the first 5 hidden states, they can recover the 4th and 5th tokens in a similar manner, and finally, they can recover the 6th through 10th tokens using all 10 hidden states. Overall, the provider can recover the first 10 tokens in a total number of attempts that adds up based on the gaps between the known hidden states. In general, If the provider has access to certain hidden states, they can reverse the first tokens in a number of attempts that depends on the gaps between those states. Although this attack seems powerful, the number of attempts can be very high, making it impractical. For instance, the largest term in our example is extremely large, making it unfeasible for any adversary to search through. We define a threshold, called the vocab matching threshold, which indicates the maximum number of attempts an adversary can realistically make. This threshold can be adjusted based on specific security needs. Given that the vocabulary size in modern language models is typically around 100,000, the threshold for most adversaries is likely to be low. Finally, we note that our generalized attack requires stronger assumptions than the basic attack to be effective. While the basic attack only needs to avoid collisions in a limited number of attempts, our generalized version requires this across a much larger number of attempts. However, we assume that collisions are unlikely in our security analysis, treating this generalized attack as a theoretical concern. Section Summary. In this section, we generalize the vanilla attack to scenarios where not all hidden states are available, demonstrating that while recovery of all input tokens is not guaranteed, we can still recover a subset of tokens based on the hidden states received. We define a vocab matching threshold, which indicates the maximum gap between known hidden states that an adversary can exploit, and note that this generalized attack requires stronger assumptions than the vanilla attack, making it primarily a theoretical concern. Section Cascade. Token-Sharded Multi-Party Inference. In this section, we introduce Cascade, a new statistical multi-party inference scheme that addresses the vocab matching attack we discussed earlier. We found that this attack could be adapted to reverse tokens from token-sharded hidden states, but its effectiveness diminishes with larger gaps between revealed token indices, making it impractical for certain sharded hidden states. Our defense against this generalized attack leverages token sharding, allowing us to maintain standard computation without significant overhead or performance loss. Unlike secure multi-party computation methods, we do not need to make approximations for nonlinear calculations, and there is no need for trusted party interactions during inference. Cascade takes advantage of the self-attention mechanism in transformers, where only this part interacts among tokens in a sequence. Other components treat tokens as independent elements. In our approach, comp nodes handle subsets of tokens and perform most batch operations, while separate atom nodes manage self-attention using projections of sharded hidden states. The atom nodes then send partial attention outputs back to the comp nodes, which can reconstruct the full attention output. Next, we define the notation and protocols for Cascade without specifying a sharding setup. In the security analysis section, we will clarify the sharding scheme based on a thorough security evaluation. For sharding and notation, we define several parameters: the number of attention heads, the number of key value heads, the total token count, the hidden dimension, and the attention hidden dimension. We implement three types of sharding along the token dimension: hidden states, query states, and key value states. This involves dividing token indices into distinct subsets for each type of state. We also shard positional embeddings and the attention mask, which are set before inference, along with the masked logits and attention output. In practice, we can symmetrize the sharding of query and key value states. This is necessary to ensure that every index pair is covered by some combination of query and key value shards. Since the query and key matrices are linear projections of the same hidden states, we can equate the sharding of queries and keys without compromising security. Consequently, we will use the same notation for both, simplifying our representation of sharded intermediate states in the model. Section Summary. In this section, we introduce Cascade, a statistical multi-party inference scheme that defends against vocab matching attacks by utilizing token sharding of hidden states, allowing for efficient computations without cryptographic overhead or performance degradation. We also define the sharding notation and protocols, emphasizing the symmetrization of query and key value sharding to maintain security while optimizing the attention mechanism in transformers. Section Single Layer Pipeline. In this section, we describe how Cascade functions for a single layer of a large language model, LLM. We have two types of nodes that store our defined sharded states, comp nodes and atom nodes. We initialize a certain number of comp nodes and atom nodes, which we label as comp node with index I and atom node with indices j and k. Cascade divides the inference process for a single layer into three parts: a prepass handled by comp nodes, an attention pass managed by atom nodes, and a postpass again by comp nodes. We will detail these processes in the following subsections. During the inference at layer L, each comp node starts with a specific hidden state and ends with an updated hidden state for the next layer. This output becomes the input for the next layer's inference, allowing us to follow the defined process for all layers. After the final layer, the comp nodes apply the language model head to produce logits, which are then used by the comp node responsible for the last token to generate the next token's embedding. This embedding is sent back to the comp node for the next token index, and the inference process continues to generate subsequent tokens. We can enhance this process using key-value caching, which we will discuss in the appendix. Next, we explain the components of the prepass, attention pass, and postpass in Cascade. All operations related to sharded slicing and concatenation are set up at the node initialization. We assume that all atom nodes wait for the comp nodes to complete the prepass before starting the attention pass, and similarly, all comp nodes wait for the atom nodes to finish the attention pass before proceeding to the postpass. In the prepass, each comp node begins with its sharded hidden states and applies layer normalization if needed. It then projects these states to obtain the sharded query, key, and value states. The comp node applies rotary or positional embedding to the query and key states using sharded positional embeddings, which it can generate during setup to avoid communication delays. Finally, it returns the query, key, and value states. After the prepass, each atom node receives the sharded query, key, and value states from the comp nodes. By concatenating these states across all comp nodes, the atom node forms the complete query, key, and value states. For the query, this involves sorting and concatenating the relevant elements. The atom node then computes the attention scores using matrix multiplication and stores the necessary maximum values and exponentials for the postpass. It applies the softmax function to the attention scores and performs value multiplication to obtain the final output. All relevant data from this process is returned as specified. Section Summary. In this section, we describe how Cascade operates within a single layer of a large language model, LLM, using two types of nodes, comp nodes and atom nodes, which handle sharded states. The process involves a prepass by comp nodes to prepare query, key, and value states, followed by an attention pass by atom nodes to compute attention scores, and concludes with a postpass by comp nodes to finalize the output for the next layer's inference. Section: Postpass. In this section, we describe the postpass process. After the attention pass, each comp node receives specific outputs from each atom node. These outputs are slices of the attention pass results along the second-to-last dimensions. For each fixed index, we concatenate the rows of these slices across all indices to form new combined results. Next, we aim to merge these results over all indices into the sharded output of attention. We use a specific method that involves softmax operations and matrix multiplication, treating each head separately. The terms we sum are not directly known to the comp node because the slicing occurs after applying softmax. To address this, we note that we can simplify the summation using element-wise multiplication and maximum values from the results. This ensures numerical stability, as the values we work with are constrained. Ultimately, each term in our calculations is now known to the comp node, allowing it to perform a weighted average of the results from the atom nodes, using weights derived from the outputs. Finally, we apply an O projection to obtain the final attention output for the specified row indices. Next, we analyze the security properties of our system, Cascade. Since we do not use cryptographic methods, we focus on statistical security. The security depends on implementation parameters, including the number of participating nodes and the sharding strategy. We assess potential information leakage by examining isolated computational stages. Throughout all stages of Cascade, no information is exchanged during computation, meaning any leakage arises from the initialization stage. As more nodes participate, each node accesses fewer tokens and hidden states, complicating the reversal of the full input. The choice of sharding also influences this difficulty. We specifically consider C, delta, sharding strategies, which have certain security advantages. We define a C, delta sequence and focus on these strategies because they meet several security requirements. However, we acknowledge that other sharding methods might be more suitable depending on the context. We will further investigate potential leakage to comp nodes and from shards, as well as leakage from specific components to atom nodes in subsequent sections. Section Summary. In this section, we describe how each comp node processes outputs from atom nodes after the attention pass by concatenating and combining results to produce a sharded output, while ensuring numerical stability through element-wise operations. We also analyze the security properties of our Cascade implementation, highlighting that information leakage is minimized by the sharding strategy and the number of participating nodes, with a focus on C, delta, sharding strategies for enhanced security. Section. Layer 0 Comp Node Hidden Security. In this section, we first examine the security of comp nodes at layer 0 of our scheme, where each node holds token embeddings of the input prompt. Since these embeddings can be easily converted back to their original tokens using a lookup table, we determine that Cascade should not be employed when the security of each token is critical. If we need to ensure individual token security, we can combine Cascade with secure multi-party computation, as discussed in the appendix. When a comp node has access to some of the token embeddings, the ability to reconstruct the full prompt is limited by the entropy of the distribution. Although we cannot directly compute this distribution, we can estimate it using masked token infilling techniques similar to those used in training models like BERT and RoBERTa. We utilize the advanced modern BERT large model to analyze this distribution under a specific sharding strategy. By sampling 200 instances from FineWeb Edu, we calculate the Rouge L score for token generation. Our findings, illustrated in a figure, show that the Rouge L score decreases as both parameters increase, indicating that good security is achieved when both parameters are at least 8, leading to a delta of at least 64. Next, we focus on the security of comp node hidden states at deeper layers of the language model. We explore whether we can choose a sharding strategy that protects against the attacks we previously described. Our defense against vocab matching attacks involves ensuring significant gaps between token clusters in the sharding scheme. In each shard, the distance between clusters is determined by the parameters, and the cost of executing a vocab matching attack increases exponentially with the maximum gap. We can adjust our parameters to ensure that this gap exceeds a certain threshold, effectively preventing such attacks. We also consider learning-based reversal attacks. While hidden states may not be as easily reversible as token embeddings, the propagation of information through attention mechanisms might make infilling tasks easier at deeper layers. To test this, we fine-tune two models on masked input sequences, treating this as a worst-case scenario where the adversary knows our parameters. We implement a bidirectional mask for training and evaluate the models on their hidden states. Our results show that when our parameters are set appropriately, the Rouge L scores for reconstructed prompts indicate significant difficulty in reconstruction. We observe similar trends in blue scores, confirming that security improves as we increase our parameters. For certain values, we find that reconstruction becomes nearly impossible. We also investigate the impact of different hidden layers and find comparable or improved security across various parameter choices. Section Summary. In this section, we analyze the security of comp nodes at layer 0, concluding that while Cascade is not suitable for scenarios requiring high token security, integrating it with SMPC can enhance security. We also explore the effectiveness of sharding strategies against various attacks, finding that increasing parameters like C and alpha significantly improves resistance to both vocab matching and learning-based attacks, as evidenced by low rouge L and blue scores in our experiments. Section: Comp Node Full Security. In this section, we examine the security implications of the shards represented by the variables m, e, and u. Our main theorem indicates that to maintain security against vocab matching attacks, we need a sharding scheme, like C, delta, sharding, which ensures there are significant gaps between clusters of indices. If these gaps are not large enough, an attack can be executed at layer 0, potentially exposing more tokens to a node. Specifically, we state that if the attention mask is unidirectional and we define a vocab matching threshold, then to thwart the generalized vocab matching attack, every gap between clusters of consecutive indices must be at least as large as this threshold. To illustrate, we fix an index and consider the ordered set of indices. For any index in a certain range, we find that the output depends on both known and unknown tokens. Since the node knows all tokens from a specific set, the function we analyze only relies on unknown tokens from another set. If there are fewer tokens than the threshold in any gap, the node can explore all possible sequences of these unknown tokens and match them to known values, thus recovering all tokens in that gap. Therefore, to prevent this attack, we require that each gap be at least as large as the threshold. This means that clusters of consecutive indices must also maintain this minimum gap size. We note that the C, delta, sharding condition is satisfied if the difference between delta and C plus 1 is at least as large as the threshold. This requirement is slightly stronger than what we previously established, which only considered leakage from another variable. In our appendix, we further argue that having a sufficiently large delta minus C plus 1 is adequate for security at layer 0 by showing it leads to a complex linear program. Section Summary. In this section, we demonstrate that to maintain security against vocab matching attacks in our sharding scheme, it is essential to ensure that the gaps between clusters of consecutive indices are sufficiently large, specifically at least equal to a defined threshold, rho. Our findings indicate that the C, delta, sharding approach can satisfy this requirement, thereby enhancing security at layer 0 against potential information leakage. Section: Atom Node Full Security. In this section, we analyze the security of Atom node. We note that the sharding for S and T is equal, so we will focus on S sharding, assuming T is treated the same way. For a given R sharding, there are various options for S sharding. One approach is to make S and R the same, allowing each Atom node to access both query shards from comp node _j and key value shards from comp node _k. However, this leads to each Atom node having access to twice as many Q, K, V rows as each comp node, which we want to avoid. To limit this access, we suggest further splitting the Atom nodes. We can define beta as m times alpha and divide each R_I into m shards, labeled R_I1 to R_I m. The S shards are then defined as S_m I1 plus x equals R_I x for all I and x. This method maintains pairwise coverage while reducing the number of tokens each Atom node can access by a factor of m. This split also increases the total number of Atom nodes, represented by beta squared, by a factor of m squared. We still have some flexibility in how we subdivide R_I into subsets R_I x. Assuming R_I follows a specific sharding scheme, we suggest that R_I x includes elements from sorted R_I at certain indices. For instance, if we have specific values for alpha, C, delta, and n, we can calculate beta and define the sets of tokens that each Atom node can access. By structuring S this way, we prevent vocab matching attacks. Since the elements in each R_I x are spaced apart by delta, and each S_I xjy combines elements from different R_I x, we ensure that there cannot be 3 consecutive elements in S_I xjy if delta is greater than 2. Additionally, the largest gap between two elements in S_IXJY is at least half of delta, making vocab matching attacks impractical for large delta. To evaluate security against learning-based attacks, we conducted experiments using our proposed scheme with different values of M. We focused on a specific model and layer due to computational limits, expecting similar results for other models. Our findings indicate that while M equals 2 yields a higher Rouge L score compared to comp nodes, the score for M equals 4 is comparable. Therefore, we recommend using M values of 4 or greater for enhanced security. Section Summary. In this section, we analyze the security of ATN node by proposing a method to reduce information leakage through an M split of ATN nodes, which decreases the number of accessible tokens while maintaining pairwise coverage. Our experiments indicate that using a split factor of MGEQ4 enhances security against learning-based attacks, as it effectively prevents vocab matching vulnerabilities. Section: Collusion Resistance. In this section, we discuss collusion resistance in our scheme. Most secure multi-party computation (SMPC) methods fail when nodes share information. For instance, in a two-party additive secret sharing, a private value is divided into two parts held by two parties, allowing them to reconstruct the original value if they collaborate. We analyze the collusion resistance of our method, Cascade, and find that when comp nodes and ATN nodes collude, they can access all their token shards. This sharing reduces the gaps between clusters, making it easier to match vocabulary, which is a concern for our security. The exact limit on collusion depends on security settings, but generally, Cascade needs many non-colluding nodes to remain secure. Next, we outline the communication and computational costs associated with Cascade. We assume ideal communication conditions, with a consistent bandwidth and latency between nodes. We define the size of each element in bytes as F for theoretical costs. We first estimate the costs in Cascade. We find that there is minimal computational overhead compared to standard inference. We provide evidence for this in our benchmarking section. Regarding communication, we derive formulas for the byte and time overhead, noting that the only sharding parameter affecting this is beta, which scales linearly with it. Therefore, minimizing beta, which also reduces the number of ATN nodes, minimizes byte overhead. Communication time is also reduced when the maximum sizes of certain partitions are minimized. When we divide tokens evenly among comp nodes, we achieve optimal communication time. We then evaluate Cascade's real-world performance using the distributed computing framework RAY. Our experiments run on paperspace machines with specific CPU and memory configurations. We compare Cascade against two recent SMPC methods, MPC Former and Puma. For MPC Former, we adjusted its implementation to use public weights to align with our setup. We perform inference on two models, BERT base and BERT large, with a fixed input size, repeating the measurements to account for variability. Our results show that when comparing Cascade with a single node to standard inference, the runtime is slightly longer, but still within the confidence interval of standard inference. When using RAY, Cascade is about 3 times slower than without it, mainly due to overhead from the framework. We also test Cascade with different configurations and find that it remains significantly faster than both MPC Former and Puma, even in its slowest settings. The increase in runtime as we scale up the number of nodes appears to be sublinear, suggesting efficient parallel computation. We plan to explore larger configurations in future work to further validate our findings. Additionally, we checked the total communication in the simplest case and found it closely matches our theoretical estimates, with only minor increases due to framework-specific factors. Our comparative analysis shows that Cascade is much more efficient in terms of total bytes transferred compared to the other methods. Section Summary. In this section, we analyze the collusion resistance of Cascade, noting that colluding nodes can access combined token shards, which affects the feasibility of vocab matching and necessitates a large number of non-colluding nodes for security. We also evaluate the communication and computational costs of Cascade, finding it to be efficient in comparison to other SMPC schemes, with minimal overhead and significant performance advantages, particularly in terms of bytes transferred. Section: Scalability. In this section, we tested how well Cascade scales with the size of the model. We conducted a forward pass using an input prompt of 128 tokens, with a setting of alpha equal to 2, and without using M-splitting. We repeated this process 100 times. Our findings, shown in the table, indicate that the runtime increases at a slower rate than the model size, which suggests that Cascade can efficiently scale to larger modern language models. Additionally, we noted that Puma took about 300 seconds for a complete forward pass on Llama 2 to 7B, while Cascade performed over 20 times faster.